In this section, we'll be taking a look at the VPLS concept objective of the JNCIP SP exam. For more detailed coverage of this topic, please check out the Juniper courses AJSPR, JL2V, and JL3V.
So far, we've examined how we can deploy point-to-point virtual links between customer devices within a service provider environment. Well, what if we want to deploy multi-point to multi-point links? What if we want to emulate an Ethernet segment within the MPLS network to provide a broadcast segment interconnecting multiple sites to a given customer? Well, to do this, we can turn to VPLS, or Virtual Private LAN Service. And this is what we're going to examine in this video here. So remember from previous videos that we can use either BGP or LDP, or a combination of the two, to signal these point-to-point virtual links between customer devices within an MPLS network. With VPLS, we actually utilize exactly the same signaling as these methods. It's just that we do it and we create a full mesh of virtual links between all of the connected sites. And with this full mesh of virtual links, we can then start to emulate broadcast medium between those various sites. Let's examine how we can use these different signaling mechanisms to provide this full mesh of virtual links to provide this virtual private LAN service. So first off, let's examine BGP. So we used BGP to signal layer 2 VPNs. And what happens with BGP signaling for layer 2 VPNs? Well, say we have a virtual circuit running between PE1 and PE2. Remember, we're exchanging NLRIs that are describing site IDs and label bases, the base MPLS label and label offset values. And using these combination of values, we're calculating the MPLS value to use on transmission and receipt of packets between these two devices for this virtual circuit. So how do we change this behavior to facilitate a full mesh of virtual circuits? Well, we don't really need to change a huge amount, is the answer. BGP has this nice dynamic already that the NLRIs that we're announcing are going to reach all PEs that are connected to our BGP mesh, just by the nature of BGP flooding. So all we need to do is change the configuration slightly. So instead of binding a particular site ID, a particular interface, to a particular remote site ID, we remove that binding and we're saying that any site is allowed to form virtual circuits to any other remote site within that identified VPLS domain. And this basically allows us to form this full mesh of virtual links. So VPLS is actually easier to configure on Juniper devices than configuring the layer 2 VPN virtual circuits. We're just removing that binding of local interface to remote site ID. So what about LDP signaling? So we can absolutely use LDP signaling to form this full mesh of virtual links. However, there is more manual configuration required, because remember, with LDP signaled virtual circuits, we're needing to identify the remote PEs and the identifier on those remote PEs to form the virtual circuit. And we would need a full mesh configured, so that's more configuration. If we wanted to reduce the amount of configuration required, we could again turn to LDP auto discovery. So that is that we're using multi-protocol BGP to advertise the PE endpoints that we're then going to be bringing up targeted LDP sessions to form the virtual circuits. Remember that if we're using LDP alone, this is going to be FEC 128. If we're using LDP auto-discovery, this is FEC 129. So imagine now we've used one of these three signaling mechanisms to establish our full mesh of virtual links. We then need to emulate the behavior of a learning bridge within our MPLS core. So how do we do that? Well, basically, every PE acts as a learning bridge. So it's going to be learning where MAC addresses are located, and it's going to be flooding when it doesn't know where to send a MAC address, much like a learning bridge, much like a switch does. We'll examine this in a lot more detail in the next video. So we now have our full mesh of virtual links that constitute our VPLS. We now need to see how frames get forwarded across these virtual links to the destination hosts that are connected to this virtual Ethernet segment. So let's now imagine that this VPLS, this segment, has just been configured for the first time, and we have two hosts connected to it, host A and host B. How are we going to get frames between these two hosts? So let's take a look at this from the perspective of host A and PE1. So host A is sending a frame with a source MAC address of A and a destination MAC address of B. This frame arrives on PE1. And now what we're going to be doing in a VPLS is that every PE, independent of each other, is going to be acting as a learning bridge. It's going to be building its own MAC table. And so this is so that a PE can know where MAC addresses are located, so he can unicast forward frames to those MAC addresses rather than having to broadcast them. So frame source MAC A, destination MAC B arrives on PE1. He now puts an entry in his MAC table associating MAC address A with the interface over which he received that frame on. He doesn't know where MAC B is located, so he's going to flood the frame out in the network, obeying split horizon rules. So the split horizon rules are there to help us prevent switching loops. And the first split horizon rule is any frame received from a CE interface can be forwarded out to any other CE locally connected apart from the interface to which it was received over, and it can be forwarded to every remote PE. In the opposite direction, if we receive a frame from a remote PE, we will send that frame out to every local CE interface, but we will not forward that frame across any virtual link to any remote PE. And these split horizon rules reduce the occurrence of switching loops in a VPLS domain. So let's now turn back to our example. We're flooding this frame out across all the virtual links from host A to host B. This frame arrives on PE3, it's locally forwarded, and it eventually arrives at host B. Host B is likely going to now reply to host A. And we're looking at things from the perspective of PE1. So let's say that this frame is now forwarded across the MPLS core. It gets to PE1. This frame is going to be encapsulated in MPLS. We're going to need to remove this MPLS encapsulation and then have a look at the inside of the frame so we know how to forward it, and so that we can also perform MAC learning, but from the core side. And to do this, we use virtual interfaces. either an LSI interface or a VT interface, a virtual tunnel interface, depending on some extra configuration or some platform-specific behaviors. But we are always using one of these interfaces. And basically what this allows us to do is we have a first pass through the forwarding plane that removes those labels or label, and then we have a second pass through the forwarding plane that allows us to take a look at the source and destination MAC address. The destination MAC address to allow us to forward the packet. The destination MAC address in this case is going to be host A. We have that binding there already, so we can unicast forward it to this CE. And the source MAC address, so that we can build the MAC table further on our PE, so that we know where host B is located. And when we're performing this binding from the core side, we associate that MAC address B, with the particular logical tunnel interface that we have that's associated with the MPLS label that's associated with the virtual link connecting to the PE that has the remote host on it. And so this allows us to build our MAC address table, which allows us to unicast forward frames between hosts that are connected to our VPLS domain. In this video, we took a look at frame forwarding and MAC learning within VPLS.